Okay, so um, I'm going to show a few slides with the results from uh, several experiments. I will try to summarize the main findings and also the main ideas. Some of the slides are, self-explanatory, so maybe I will skip these ones to have a shorter video and also, well, try to focus only on the main aspects. So we can always go back to them on a need-to-do basis. Okay, so mainly two topographies, the smoothed topography, the one that I have called the idealized or ideal one experiment, and the second one actually was your suggestion to do a longer or what I call extended margin experiment. For this one, we also have higher vertical resolution case with 60 levels and different stretching so that we have much finer resolution close to the bottom and no beta case. So most of the time we are going to be referring to time averages, and these actually concern the second year of a 2-year simulation. So if we first look at the surface flow, so the average surface flow between the two experiments, so the smoothed topography and the extended margin, it's actually interesting that close close to the entrainment zone, the surface flow is not as very different between the two experiments. So we have mainly two inflow branches, so one close to the coast and one more offshore in both cases. And we also have the development of an offshore flow also here in both cases around 8 West. However, the main point is that west of 8 West, it is precisely the point where these two topographies become very different. And to me, the single most important results of this extended margin experiment, which is quite interesting, is the fact that the flow, the offshore flow, starts to separate or you start having an offshore flow, a clear offshore flow around 8 West. So very early and completely independent of any cape or steepening or changes or drastic changes on the topography. So topography here, topography here is very simple, and you also have the generation of the offshore flow. Okay, if we look at the estimates of the entrainment among the different experiments, we don't have so many differences. I think the differences are more in detail. The amount is, well, approximately the same, so we have around 0.4 to 0.7. Most of the entrainment occurs very close to the strait, so between 6 and 8 West maximum, although the bulk of entrainment actually occurs east of 7 West. Also, one of the very important points here is that in the case of the higher resolution experiment, we have a much smoother we have much smoother fields in all variables, and also we have much smoother pattern of W star, of the entrainment velocity. Okay, so if we compare the circulation on isopycnal levels, or if we look at the circulation on isopycnal levels, so what we do here is we not only average in time, but we also average on the vertical in different layers. And so we have here the lines correspond to the stream function of average flow on each layer, and vectors is just the mean velocity on that layer. So the most important point here is that we indeed see the generation of the cyclonic flow, but interestingly, it's not right over the entrainment area, but somewhat displaced offshore and to the north. So that's also a clear pattern here in the different experiments, and becomes much clearer in the along this experiment with the extended margin. Okay, so if we repeat the same exercise of calculating the budgets through the volume fluxes, so the trying to estimate both entrainment and the transport through volume budget above different isopycnal levels. So that's what we do here. So we have a bit more of transport in the extended margin experiment than we did have in the smooth topography experiments. So it's a bit higher, although not much. So if we compare the values that we have up to 8 west, so around here, so we have somewhat larger outflow and inflow, so a larger circulation over the extended margin experiment than we had at 8 west. So there is a difference, a clear difference in topography between experiments in what concerns the generation of flow and recirculation. Okay, in any case, if we do the same estimates for the entrainment, so I recall that what we do here is like doing a budget above a given isopycnal. So we compute everything that goes in one direction and what is recirculating, and then we extract the value of the inflow itself. And so the difference should correspond to the flow that is actually going vertically from one isopycnal level to the other. And the estimate is always about 1.5 Sverdrup. So it's approximately the same with some differences, of course, but not very significant among the different experiments. So this is also a robust result. And also the fact that most of entrainment really happens above 37.6 isopycnal. So let's have a look to the vertical structure in the different experiments. So we have the smoothed topography and the extended margin and the extended margin with higher vertical resolution. So I recall that well, the red lines correspond to the outflow and the blue ones correspond to the inflow, or the flow into the strait. So we're very close to the coast, so we have part of the inflow and offshore. So we have inflow, outflow, and so we have some clear recirculation in the upper levels above 27.2 or 27.4. we don't see as much as in, we don't see so much inflow here in the extended margin experiment as we see in the smoothed topography. I remember that these sections where the position of the sections is somewhat different. So in the smoothed topography, this section number 3 is actually zonal, whereas the section number 3 here is not totally zonal. And since we have the early separation of the flow, so we don't see as many inflow in the vertical structure here in the sections of the extended margin experiment. So in any case, so we see some clear cyclonic circulation at the surface, and we also see some significant differences between the extended margin and the extended margin with high vertical resolution. So increasing the vertical resolution close to the bottom indeed makes a significant difference. So it looks like we have more concentrated flow, and we even have higher recirculation. So something that we have to have in mind. Okay, so it was also your suggestion that we could kind of average in the long slope direction. And so what I did was to take information along all these sections and then average across them all. And so we have here the averaged flow. This is the longshore flow. So we see the outflow and the inflow. Here we have the cross slope flow, so the flow in this direction. And here we have the W star. So the entrainment velocity also averaged over all these sections, plotted over the cross-section flow. So the flow into the slope and out of the slope. Okay, so we still see little recirculation here, but there is some already. So we have inflow close to the coast, and then we have some recirculation already at several levels. We clearly see some overturning, some like downwelling type flow over the slope. So the flow going into the shelf and then returning in a very thin layer along the bottom. And so we have this perspective here clearer with the W star plotted. So W star actually, is positive, is negative or is significant along, a very considerable portion of the shelf along several depths. To have a better representation or a better view of this structure, of this vertical structure, what I've done was to plot all these variables in a different way. So I just computed the variables as a difference to the distance, or versus the distance to the bottom, right? So the vertical distance to the bottom. So that's what we have here. So at the beginning it's a bit weird because, well, the vertical to the bottom is not always the same everywhere, because the bottom is actually not flat, but it gives us an idea. If you look along the vertical in every point, it gives us a better idea of the structure of the flow close to the bottom. So the thickness of the boundary layer, or of the outflow, and how these things are actually organized, or how these variables actually relate one with the other. I did also on the right the not exactly the same, but something similar, but with the isopycnal levels. So I converted the information in isopycnal levels, and what we see is the same variables, so the long slope flow, the cross slope flow, and the entrainment velocity also along the isopycnal levels. In any case, what I find interesting here is that we have better resolution of what of the distribution of the W star on isopycnals, and what we see is that we clearly have a patch very close to the bottom, and we have a secondary one. So it's organized into two different patches. One which is approximately on the top of the outflow, or on top of the layer or the interface between the inflow and outflow, and the second one very close to the bottom along the contained with the cross slope flow, with the return flow, or contained within the return flow zone. So that's probably important. I still don't have anything very smart regarding this point. It's just to know that probably what matters in terms of entrainment is maybe this patch here, and that's what should be computed in separately. Okay, so I copied these figures here to this slide, so they are repeated. And the purpose is just to try to summarize the main points of the vertical structure in relationship to the cyclonic flow. So here what we have is this section 3, so somewhat here, so considerably away from the entrainment zone, and here we see the average. Not only this one is the time average. In here we have the time and a long slope average flow over the main patch of the entrainment zone. So what we see is that the cyclonic flow, cyclonic circulation will be established much more clear, somewhat away of the entrainment zone. So we have already noticed that when we have looked to the depth integrated or layer integrated circulation, so we see that cyclonic flow will be much clearer away of the entrainment zone. So if we this is the old water column, and this one is the intermediate layers between 27 to 27.8, and so we see the cyclonic flow here already clear away of the entrainment zone. So if we go back to these sections, so that's what we see. It's much clearer already away of the strait. Anyway, close to the entrainment zone, we see it start developing. So my interpretation of this structure here is that development, and for some reason it starts to be clearer more in the offshore zone than in the inner part of the shelf. I don't know, probably in association with the presence of the inflow, the coastal inflow current. And it starts to be also clearer on top of the 27 0.6. That's where we start having this circulation, so an excess of outflow on top of 27.6. And even away of the strait, that's what we see as well. So most of the recirculation, right? Most of the recirculation actually happens on top of the 27.6. And so that's also, if we look to the distribution of the entrainment velocity in terms of isopycnal, so we see that indeed the most of it occurs above the 27.6, so approximately between 27.6 and 27 or 27.2. So that's where most of the entrainment actually happens, and it's above these levels that we shall have the circulation. And so the interesting point is that you have the circulation, the cyclonic flow will be established somewhat away of the entrainment zone. It starts closer to the entrainment zone, and it starts in the deeper levels. And right from the beginning, you have the establishment of this kind of asymmetry. So the inflow is shallower than the outflow part. So I've tried to do this is a very simple thing, maybe even a bit naive, but at least helps us with this interpretation of the what I call the asymmetric plume behavior. So if we look at the two-layer ideal case of entrainment, so this is this conceptual model where we have a surface given a isopycnal, and we have concentrated entrainment along some isopycnal, and so we have a sinking of the denser flow, so we have negative entrainment velocities somewhere here, and you will have a response of the upper layer, a cyclonic response of the upper layer, so the classic beta plume paradigm, if you want, right? Okay, so what I do think it might be happening in the symmetric case is if you have the entrainment happening across a range of isopycnals, you will have always the denser flow sinking with the denser flow will always sink to the slope. You also have the effect of the Ekman draining. I don't know if this is the direct cause of the sinking. So probably part is just driven by buoyancy, but also as soon as the flow reaches the bottom, it will also be drained downslope by the Ekman transport. And also ultimately the thermal wind effect will favor the vertical shear in velocity. So that's the way I think that the mean flow will end up adjusting. But well, probably the reality is much more complex than this simple scheme. So in parallel with the generation of this flow over topography, as we have seen already before, so I've already mentioned it earlier that very soon, around 8 West or even sooner, we have the generation of offshore flow. So this is actually kind of the very beginning of what we call the Azaris current. So it's a meandering flow actually into the strait. So the interesting thing is the fact that we have the generation of this flow independently of any topographic feature, right? So even in the extended margin experiment, you have you have it there. So that's a very interesting and important result because even in the smooth topography, we can see it forming here. But since the topography then is bending also around 8 West, it's not completely clear if this structure here is a completely, it's an offshore flow independent from topography, or it's somehow also associated with the flow that is being developed over topography. So what I think it might be occurring is the generation of flow over topography, and also something the splitting of the flow occurring very early, the splitting and development of the well, let's call it the Azores current occurring very early. So one of the comparisons we have been doing was so I've also tried to I've also did an experiment without no planetary beta effect, and so this is the mean surface flow for the two experiments. Unfortunately, I should say that these two vector fields are not properly scaled. So although the no beta experiment seems like a stronger flow, it's just a matter of the scaling of the vectors. So please, I have to do that, of course, but for the moment, just look at the flow structure, not the intensity itself. Okay, in any case, so what we have here is that in the no planetary beta effect, we can see also kind of a cyclonic circulation, right, in the cyclonic flow, and a strong inflow somewhere around here. But this is like more like the envelope of kind of a bulge of cyclones that tend to develop and remain somewhere there. Whereas in the case of the central experiment, or the beta case, the case with the beta effect, so we have the development of these structures, of this meandering, like meandering jet, that I did added this line just to mark it. And this is clearly away from the strait, so we have this separation, right? So we might have a separation occurring very early, and this actually occurs in the beta topography experiment. Sorry, in the planetary beta experiment, and it's not occurring in the no planetary beta experiment. So my first idea was that there would be some process, in connection with the interruption. Well, actually, I don't have a micro here, and sometimes it gets noisy, and so I had to interrupt. Okay, so So what I've done next was to take a look to the first moments of development of the flow, and to analyze the mesoscale, and to see how if this separation could be somehow associated with eddies or any other process that could be um, visible. And so I did a couple of videos that you can see in the cloud, um, and actually they show the relative vorticity, well, scaled by planetary vorticity, um, or normalized by planetary vorticity. And in the next slides, I will show um, these vorticity fields, the synoptic fields uh, for the experiment with the planetary beta and without the planetary beta. So my idea was to mostly look at the generation of eddies and how they behave, and if they could have any kind of influence on the establishment of this offshore flow. So this is a synaptic shot, after about 300 days. And so we always see this trail of cyclones generated. They actually are generated somewhere over the entrainment zone, and then they kind of drift along the slope. They are sometimes associated with anticyclonic circulation in deeper levels. So you have also the generation of Medi-like features in deeper levels, and this is very clear in the experiments with higher vertical resolution close to the bottom. So you see the generation of very nice Medi-like structures in these experiments. And so you have the red line, and we can see the meandering and the development of this structure, of this offshore structure, already in this synoptic shot. So you can have a look in the animations there, in the videos, but well, we can see it here. And so the point is that it's not it's a feature that is not a timing feature like you see here. Of course, here it's much clearer in the timing, but we see it on the synoptic shots. Okay, so being formed here. And actually, if we look at the case with no planetary beta, it is actually missing. So you don't see a clear flow offshore. So in terms of generation of eddies, of cyclonic eddies, you don't have as many differences, right? But if we flip from one to the other, the cyclone eddies look like they are stronger in the no planetary beta case, but in the end, the cyclonic, the behavior of the eddies is not so different. So they tend to propagate along the margin, and also slowly drift offshore, and clearly having no planetary beta case. So these are they should be driven by topographic bit, and also I mean by interactions between eddies. Right? So I don't expect. So we don't have the formation of this offshore flow right at beginning in the case of no planetary beta. So in summary, we the idea is that what is the nature of this offshore flow generating very early in the simulations. So here we have a comparison between the flow with higher vertical resolution, where this offshore flow is even more clear, than in case of the basic case. So the thing is, well, the question now. So what is the nature of this offshore flow? So we see that there is, at least apparently there is no clear connection with the eddies. So we have eddies as well in the no beta case, but we don't have this flow being generated offshore. So what's the process of generation of this flow? Is it an early splitting of the planetary, of the topographic beta plume that we see we have seen in the vertical in the sections? So is it connected with the topographic beta processes? Is it a completely different process that is generating right at the beginning by any other interaction, like the emission of Rossby waves associated with the entrainment zone, associated with inflow? So is it something that runs in parallel, or is clearly the splitting? So they're both connected, and this is the splitting of the topographic beta plume. As Kida, actually Kida 2008, they advocate in their paper that the generation of the plume of the cyclonic beta plume is associated with topography. It's because of the topographic beta effect, but because of eddies, this beta plume actually separates from the from topography, from the shelf, and generates a planetary beta plume. But here, in this case, what we see is not the splitting of the entire beta plume, but only the inflow branch. So the remaining of the plume actually continues to propagate along the slope, right? So that's probably the main difference and main aspect that we can observe from here, is that we don't need to have any kind of difference in topography, and probably it's also might even happen independently of generation of eddies. So if I trying to summarize the main topics, or to give an overview of the point where I am at this moment, well, I could say that I think it is more clear at this moment that the fact that all experiments really develop a plume-like or cyclonic circulation like the beta plume, but you have this symmetric behavior. So that seems to start being a clear pattern in these experiments. So it is also interesting in the fact that the incoming branch seems to separate from the margin very early, near to the entrainment zone, and that occurs actually independent of any topographic feature. So you don't actually need the cape or a change in the slope, or significant change in the slope for that to happen. Of course, at the beginning, I thought that eddies should play a significant role in this separation, but it seems they are at least not the main driving mechanism for the establishment of the offshore zonal jet. So, the eddies actually move offshore, but the jet seems to be associated with meanders. They kind of have a larger scale. They are placed offshore of the eddies. So it, at least at this moment, it looks like it's kind of a different process. And it's also seems clear that the remaining part of the plume, so the outflow, continues to flow polyward along the margin, and will ultimately separate at the northern point, either by eddies or any other process. So I did try to have a little scheme here summarizing the main ideas. So we have the strait. So first of all, we have the development of a inflow coastal current. So part of the inflow actually is driven by these processes that will establish along probably by Kelvin waves along the coastal the inner shelf part. So we have the entrainment zone here, where actually the outflow starts to accelerate, and where you have this main interface between inflow and outflow. And you will also have generation of eddies, so that they propagate along the margin and ultimately separate offshore. And what we see is that we have the generation of this outflow branch quite early, independently of the cape, so very close to the entrainment zone. But interestingly, so what occurs close to the entrainment zone is mostly an overturning like circulation. So you have part of the flow that just goes directly into the strait, or is actually entrained into the outflow. And the development of horizontal circulation actually occurs a little bit offshore and to the north. So you have the cyclonic plume being generated or starting to appear in the mean flow, not over the entrainment zone. And then you have kind of a bulge of cyclones that kind of accumulate here, and in the end you have the reinforcement, or maybe you actually have a larger cyclonic circulation here, maybe because of the accumulation of all these eddies. So, but that's still pretty much a speculation what I'm doing here. So mostly the important things are actually the development of this symmetric plume, and also the splitting of the plume. And so it contributes to a wider, so different the different place for the establishment of the zonal jet, the incoming part and the outcoming or outgoing part of the outflow.